as is usual, let's start off by taking a look at the homework. I want to get you all through everything that you need this for homework to do. But well, so we're going to talk about separability today. Suppose first off that you have a field of characteristic or a field K of characteristic P bigger than 0. So if the degree of f over K is n and P does not divide n, show that P is separable over K. And informally, what it means to be separable is if you have an irreducible polynomial that has a root in f, then the roots have to be not multiple roots; they have to be single roots. So in other words, you can't have a root that has a power of it. I'll make that a little bit more formal in a moment. Number B, if U and F is algebraic over K, then U is separable over K if and only if K adjoined with U is equal to K adjoined with U to the P to the N for all n greater than or equal to 1. This one's very good to do at least one direction by induction. Number 2, let K be a finite field and F an algebraic closure of K. I'm going to tell you what a finite field is today. We'll get to, or I'm going to tell you what algebraic closure is today. We'll get to finite fields pretty soon. Show that the Galois group of F over K is abelian, right? So that is to say that when you compose any two automorphisms, it doesn't matter what order you do it in. When you look at the algebraic closure of a finite field. And number B, show that every non-identity element of the Galois group is an infinite order. So it's an abelian group, and every non-identity element has infinite order. And in number 3, let F be an extension of K and U be elements of F such that U is separable over K and V is totally inseparable over K. Show that K adjoined with U plus V is the same thing as K adjoined with U comma V. So you can just use U plus V to get that sort of double extension, if you will. And also show that KUV is equal to K adjoined with U times V if both U and V are not 0. Okay, so any questions before we move on? All right. So we'll get you through at least separability. Learn what that is today. Simple. That was the word I was struggling with. So the last thing that we did was we talked about these equivalent conditions on what it meant for a field to be algebraically closed. And I'll be honest with you, I'm going to wave my hands at some of this. Here's kind of a big theorem. No chalk, wet chalkboard. Theorem. Every field K has an algebraic closure. Field K has an algebraic closure, and any two algebraic closures of K Okay. So I am not going to go through this. I'll tell this to you intuitively. Here's what happens. What you can do is you can take your field K and look at Kx, right? Now take all the irreducible polynomials in Kx, right? And adjoin roots of all of them. And it turns out that you can build this, it's Sloan's limit kind of thing. And it turns out that this field is algebraically closed, right? By some of the results we had last time. You take every polynomial in K, you join all the roots. This is very sloppy, but join all the roots of this, and what you get is an algebraic closure. One of the proof of this is mostly set theoretic and mostly kind of logic, which is I'll skip over here. Let me ask you this: how many of you have heard of the field of surreal numbers? Everybody's heard of surreal numbers? Kind of weird. It's actually not a field. Do you know why?
It's not a set, right?
That's right. It's too big. It's not a set. And part of the proof of this is showing that actually, when you construct this algebraic closure, it's actually a set in the first place, and it is, right? From a practical point of view, you can still sort of use surreal numbers, but they're technically not a field because technically it has to be a set, and surreal numbers are too big. That's part of the problem with this. But anyway, we'll take this. If any of you that are brokenhearted that we're not going into the logic of it, just come talk to me, and I'll be happy to work through it for you. But basically, what this is this is the splitting field of the set of all irreducible polynomials in Kx. That's how you can do this. So as a corollary to this, of course, we get that if K is a field and S is any set of polynomials in Kx, then there's a splitting field for that set of polynomials over K. We're going to come back to Galois. It turns out that what a Galois is equivalent to normal and separable. So this is one thing. Normal, what we talked about last time, is that if you have an irreducible polynomial in the base field that has a root in the bigger one, then it completely splits. So what's the separability about? Well, I want to talk about this term polynomials too. Let K be the field and f of x kx an irreducible polynomial. Then f of x is separable if f factors into distinct linear polynomials in some splitting. Splitting field of f by the way, given f of x, we can construct a splitting field, right? And it's of it is a degree no more than n factorial over k, where n is the degree of the polynomial. Yes, you can hit that middle switch. Oh, it saw you coming.
Let's take a check.
So we know that there is a splitting field of that, right? In the sense that we can find a field extension that's big enough, degree no more than n factorial times the degree of this, where this breaks down into linears. We say that the polynomial is separable if in some splitting field f of x factors as a product of I know it's going to factor in linear polynomials. Here's what makes it separable: distinct. Right. So in other words, you don't have any multiple roots. Uh, an algebraic element U and F is separable. So suppose you have F an extension field K, and if U and F is algebraic over K, then U is separable. Anybody want to take a guess as how we want to define an element to be separable? Good. If it's minimal polynomial, it's separable. If every U and F is separable, over K, we say F is a separable extension. So let me point out that a separable extension is implicitly an algebraic extension, because what you're saying is every element first and foremost has to be algebraic, and its minimal polynomial over K has to split into distinct linear factors in some splitting field. Example. D squared, D and C squared 3. Because look at radical D, right? It's a root of x squared minus D. X squared minus D has two distinct roots, right? It splits into two different linear factors. It's x minus D, x plus D, right? And this is not just true for radical D. Test it for anything in there, right? For example, if you have an arbitrary A plus B radical D, where A and B are Q, its minimal polynomial over Q is x squared. Let's see, minus minus. And the two roots of this are A plus or minus B radical D. And notice that these are distinct. You might say, well, they're not distinct if B is 0, but if B is 0, this polynomial is not irreducible anymore. Right? I guess maybe a more instructive example might be, give me an example of an extension that's not separable. No, that was separable too.
And they got a characteristic to probably P.
And look at rational functions and the variable over Z2 and the variable x squared, rational functions in just x. Notice that x is algebraic over Z2 x squared, and it is a root of this is, of course, this is a polynomial with coefficients here, right? One times Let me make this out a little bit clearer. There we go. These are polynomials in variable t, right? So that's minus x squared. Notice that in z2x squared, this polynomial is actually irreducible, right? But in the splitting field, you have p squared minus x squared is p minus x squared. So this element is not separable. So maybe I'm just too dumb to come up with a good characteristic zero example, right? However, it's going to turn out that actually any extension of fields of characteristic zero are separable, right? So that's why I immediately knew that your answer was wrong, because I knew it was characteristic zero, right? And we'll see that in a moment. So this lack of separability, if you will, is something that can only occur in positive characteristic. So let me give you the following lemma. This will be useful. And I'm gonna bootstrap this lemma into something a little bit more powerful too. Let K and F be fields. And let's say that U is algebraic. Okay. With minimal polynomial. Let's say f of x then U is separable. This way, U is separable. Okay. If and only the greatest common divisor of f of x and f prime of x. And yes, I do mean f prime of x, right? I mean the formal derivative of this is equal to 1. So who would thought all this crazy crap limit stuff that you teach in calculus would actually come up in an algebra course? So let's so this is kind of cool. This is a way you can tell an element is separable. Find its minimal polynomial, whatever it is, take its derivative. If you can take those two polynomials and run the Euclidean algorithm and get down to 1, then that element's separable. If not, then the element is not separable. Proof. Let's assume that let's assume that f of x is not separable. That is, if we suppose that U is not separable, that means its polynomial is not separable. Then what can we say? That was a typo in the name. Oh, it's U here. Then f of x is x minus U to some power n times g of x with n greater than 1. No, greater than 1, because I want it to be not separable. So that is, U is, well, actually, I guess I do need to do this. Right, because it is true that U is a root of f of x, but, it doesn't have to be that U that has the multiple root, it could be anything. So f of x factors this way in some splitting field, of k. Now, of course, if it's a splitting field, it's geometrics also factors down to linears, but I don't care. I'm just gonna keep that fun stuff over there. Now. So I can, title this YouTube video, the chain rule, the product rule, and abstract algebra, right? So what's the derivative of this? Let's see if old Jim can still calculus. Right, so we've got that here. Now, so here we've got f of x, and here we've got f prime of x. Now, notice that kx is a Euclidean domain. Right? And so the GCD, whatever it is, the GCD of these two is a linear combination of these, right? So actually, the Euclidean algorithm will give you what the GCD is, but we actually don't even need Euclidean here, we just need PID. But the GCD of these two is linear combo of f of x and prime of x. That is to say, d of x is equal to, I don't know, a of x f of x plus b of x f prime of x. And let's call this c of x, so it's not confusing the a I used earlier. And so notice that both of these terms here, notice that a is a root of f of x and f prime of x, right? Clearly it's a root of both of these because n is bigger than one. So notice that I've got at least one factor of x minus a in both of these. Then a is a root of d of x. So d of x is not one. So that establishes one direction. For the other direction, let's suppose that the greatest common divisor in f prime is d of x. F of x prime of x equal to d of x. And of course, what we want to do is prove that this is one. Well, we get a contradiction. So suppose that the degree of this d of x is at least one. Okay, so that means that d has a root So it's a polynomial of degree at least one, so in some splitting field, of f, then d has a root. Now note, that d of x, divides both f of x and g of x. So f of x and f prime of x. So this root is a shared root of right. So let's call this root something. Let's call it a. We'll call this root a. Notice that a equals this. Well, since u is separable here, f of x is separable, then f of x minus a times g of x, where g of a is not zero, right? Because in the splitting field, this separable polynomials can only appear once. And so, again, with the derivative, in this case, f prime of x is g of x plus x minus a g prime of x, and a cannot be a root of f prime, right? Because if a annihilates f prime, it certainly annihilates this. That means a has to annihilate g of x, and we've seen it's that can't happen. Okay. So this is kind of handy dandy because you can tell if an element or its polynomial is separable over k just by invoking this criteria. Now let me say something a little bit even more useful, I think. Proposition. Let's suppose K and F is an algebraic extension of fields. Oh, wait a minute, that's all I'll say. But K and F, proposition I have. Let K be a field and f of x an irreducible polynomial. If f of x is not separable, then f prime of x is 0. All right, f of x is not separable, then f prime of x, and let me say it's identically 0. Oh, so I don't mean that it's got a root. I mean, when you take the derivative of the polynomial, it is 0, period. Right? This is pretty powerful. So this is kind of a powerful thing. If you have an irreducible polynomial, if it's not separable, its derivative has to be, always zero. Let's prove this. Okay, uh, suppose, that f is not separable. I want to show zero. Well, observe f prime of x is equal to zero, or one of two things happens. Either when you take the derivative of polynomial, you get the zero polynomial, or the degree of f prime of x is less than the degree of f of x. One of those two things has to happen, right? Either the degree drops by one, or you get the zero polynomial where the degree is technically undefined, right? So, as promised, we're going to bootstrap the previous lemma. By the previous, the greatest common divisor, f of x and f prime of x is not one, right? Because it's separable. Agree? So that means there's a greatest common divisor. It's not constant. D of x divides with f of x, and d of x divides f prime of x. Because after all, it's the greatest common divisor. Well, what do we know about f of x? It's irreducible. So d of x is either 1 or f of x up to associates. That is to say, either d of x is a constant, which we've ruled out, so it can't be this, or it has to be f of x up to associates. But then f of x divides f of x. And this is impossible unless f prime of x is 0, because the degree of f prime of x is less than the degree of this. So that's kind of cool. If you have a polynomial that's not separable, then its derivative has to be identically 0. So here is a promised result that we can rip off of this. Proposition 8.4.4. Let K and F be algebraic extensions in field of characteristic algebraic. Good for me. If K and F is an algebraic extension, and the characteristic of K is equal to 0, then, F is separable. Okay, so this is the promised result. The algebraic is really just kind of technical because any extension, if you're going to talk about it being separable, it has to be algebraic. But if you have any algebraic extension of characteristic 0, it's automatically separable. So that's one worry that you don't have to worry about anymore. It suffices to show any irreducible polynomial X separable. Well, I'm doing all this here. So well, let's see here. With Ki and Kn not equal to 0. In fact, I'm not really gonna, who cares? I'm not really going to use the reducible here. Notice that f prime of x is n Kn x to the n minus 1 plus n minus 1 K n minus 1 x n minus 2 plus K1, which is not 0. Because in characteristic 0, and here, of course, greater than or equal to 1, n is not 0, Kn is not 0, so this polynomial has a non-zero leading coefficient in degree n minus 1, not 0. So this can't be a separable polynomial. It's true, it's not 0. Any questions? So that means that everything that's separable happens in characteristic P. By the way, what do you suppose the polynomial looks like? So if it's not separable, the characteristic does a polynomial that is not separable look like? Can I describe it?
Leading term has to be degree characteristic.
Well, so let's try, let's see what a polynomial might look like. So let me write down something. We'll say, and let's suppose that I don't put up any zero coefficients, right? So let me write it like this way, put my notation here. X, well, let's see. K0, plus that. Let's say K M1 X M1 plus K M2 X M2 plus K M sub T X M sub T, where, I mean, I did after all say it's irreducible, so I would want that exponent to be 0, right? And we'll have the KI's not 0. Right, so we're not wasting our time with 0. And somebody described to me,
It's P divide all begins. Yeah.
it's exactly right.
Derivative to match everybody.
That's exactly right. You need the derivative to vanish everywhere. So imagine what happens when you take the derivative. You get K M1, that's gotta be 0. If this is not 0, then this has to be 0, which means that it has to be multiplied. Right, and you can, so for example, what you could do is, a quick proof of this is assume that like M sub I is the highest, or is the largest value of M. M sub I is the largest value of these exponents that is not divisible by PI, or not divisible by P, take the derivative and that's not 0. So in other words, f of x, it has to be a polynomial and variable x to the p, right? Because everything has to have x to be it. So that's going to be useful later as well. Okay. So I mentioned this in the homework, so it'd be nice for me to define it and all. Let's say that let K inside F be an extension. U and F is purely inseparable. If it's minimal polynomial, or it's right. Is a form x minus u to the m. So this is kind of the extreme. So what we're used to, I think, is things that are pretty, so we're used to things that are separable, right? And you take the minimal polynomial and in some splitting field, you all get distinct linear roots. This is the other extreme, right? So now it's purely inseparable. If it's minimal polynomial, it's x minus that root jacked up to some power m. And by the way, as it turns out, we'll get to it in a moment, m actually must be a prime power, right? That's what we're going to get to. And the extension is purely inseparable if each, if U and F is purely inseparable. For all U and F. By the way, let me make the observation that if U is in K, then U is purely inseparable. And is separable. Right, this is a degenerate case because the minimal polynomial is that because U's already in K. So it's purely inseparable, well, by definition, and it's separable because M is one, right? And in fact, I'm gonna give you this to you without proof. Theorem 846. K and FB fields. Then U is both separable and purely inseparable. Separable and purely inseparable. If and only if U is in K. I'm gonna give you one last lemma to think about over spring break, and we'll clear this out. This is kind of like a cleaning lemma. I like to think of it this way because I like this lemma. And here's why I call it kind of a cleaning lemma. If you have an extension field, suppose characteristic K be bigger than 0 and K is inside F. If U is algebraic, so we've learned that these elements can be all kinds of things. It can be separable, it can be inseparable, it can be purely inseparable. But suppose you have any garden variety element you want, then U to the P to the N is separable over K for some N greater than or equal to 0. So in other words, if you don't like things that aren't separable, all you got to do is take your element U and jack it up to a high enough P power, and it will become separable for you, right? Which is kind of cool. Notice that if N is 0, this is U to the 1 power, right? If U is already separable, you're good to go. And of course, this is characteristic P thing, but of course, this will certainly hold in characteristic 0 as well, just taking N always to be 0 because every element is separable. Okay, any questions on that? All right, it's a good place to quit. Y'all have a good spring break. If you decide to have some real fun and do some of the homework, the finite field questions, you might have to look a little bit further. I'm gonna do finite field before we talk about how to construct the algorithm. Anyway, y'all have a good break, and we will see you on, oh, there's a math club today, which might be of interest to some of you as well. One of our undergraduates talking about some data science and her experiences as an intern. Other than that, y'all have a good spring break, and we'll see you on Monday next.